Hello and welcome to the fifth and final video of the M2 chapter, Impulses and Collisions. Exam question on the screen to get us going. A particle A of mass 2m is moving with speed 3u. In a straight line on a smooth horizontal table, the particle collides directly with a particle B of mass m moving with speed 2u in the opposite direction to A. Immediately after the collision, the speed of B is 8/3u, and the direction of motion of B is reversed. 2m there, let me call this V for now. Calculate the coefficient of restitution between A and B. So to find the coefficient of restitution, we need to know the speed of approach. Here we've got 5u, and the speed of separation. Here we don't know because we don't know V yet. So first I need to find V. To do that, I'm going to use conservation of linear momentum. 2m times 3u is 6mu, plus m times minus 2u, because it's going in the other direction, is minus 2mu, is equal to 2mv plus 8mu/3. I should state that I've taken this direction to be positive. So if we cancel the m's and simplify a bit, we get 4u here, 2v plus 8u/3. Rearrange that, v is equal to 2/3 of u, which means the direction of A has not changed. It's still going in what I've called the positive direction, this way. But that's not what the question wanted. We want the coefficient of restitution between A and B. To find that, I need the speed of separation, 8/3u minus what we just found, 2/3u, divided by the speed of approach, 3u minus 2u, which gives us 5u, which simplifies to 2/5 for the coefficient of restitution. Part B, show that the kinetic energy lost in the collision is 7mu². Part A. Part B, we need the kinetic energy before the collision. And that is 1/2 times the mass of A, which is 2m, times the speed of A², plus 1/2 times the mass of B, which is m, times the speed of B, 2u². Remember, kinetic energy is always positive, so we don't need to worry about the direction on this. That gives us 9mu² plus 2mu², for a total of 11mu². Kinetic energy after the collision, same idea, 1/2 times mass times speed, which was 2/3u², plus 1/2 times mass times speed, 8/3u², which gives us 4mu²/9 plus 32mu²/9, for a total of 36mu²/9. 36/9 is 4mu². So the kinetic energy lost is 11mu² minus 4mu², which is 7mu² as given in the question. In this video, we're going to solve problems involving successive impacts. That means more than one impact, one after the other. So a problem involving two or more successive impacts is solved by simply considering each impact in turn. It's just like having two questions put together into one big question. So you should completely finish one impact before you start the next one. Consider them completely separate events. And for your examiner, just be clear in your working when you change the final velocity of one impact into the initial velocity of the next. So a quick overview of the idea of this before we get into the numerical examples. Let's say we've got 3 spheres here. This one is going to be projected towards the other two, which are at rest. Obviously this one is going to hit this one, and that's your first impact. So if I call this A, B, and C, we consider A and B first. And we treat this as we've been doing all of the other questions. This one impacts this one, so that's before they hit, and then we find after they hit. We do conservation of linear momentum, or Newton's law of restitution, or both, whatever we need to do. Find all the information about how these two particles are moving after they've impacted. And then obviously in this situation A is going to hit B, and B is going to start moving towards C, and it will hit C. So at that point we then start looking at B and C before their impact, and you can see that the final velocity of B in this impact is going to be the initial velocity of B as it comes towards C. So that changeover from this situation to this situation, be clear where that is. And drawing diagrams like this will help, because if you write something here and then you write the same thing over here, that will help the examiner see what's going on. And then of course we'll have an after impact between B and C, and then the final velocity of A here, final velocity of B here and C here will be the situation after the two impacts. And possibly there will be further impacts depending on whether A will catch up to B after it's impacted C. So if you have three particles, it's likely to split into two completely separate problems, the only crossover being final velocity of B here is your starting velocity of B here. The rest of the video are just lots of examples and a couple of exam questions at the end. Three spheres, A, B, and C, have masses m, 2m, and 3m respectively. The spheres move along the same straight line on a horizontal plane with A following B, which is following C. So very similar to what we had here, except that instead of them starting at rest, they're all going to be moving. Initially, the speeds of A, B, and C are 7, 3, and 1 respectively in the direction A, B, C. So if I set this up in the corner here, we've got A, B, C. They're traveling in the direction A, B, C, where A has mass m, B is 2m, and C is 3m. A has speed 7, B has speed 3, and C has speed 1 initially. Then we're told that sphere A collides with sphere B, as you would expect, 7 and 3, it's going to catch up very quickly. After that impact, sphere B goes on to collide with sphere C. The coefficient of restitution between A and B is 0.5, and the coefficient of restitution between B and C is 0.25. And if you remember when we did coefficient of restitution, it's specific to the two particles. That's why it might be different between A and B as it is to B and C. So let me put that in. Between A and B, E is 0.5, and between B and C, E is 0.25. Find the velocities of the three spheres after the second collision. So I'm just going to do exactly what I said on the previous screen. We're going to take A and B first and treat this as its own mini problem, ignoring C for now. So we've got 7 and 3, and then after the impact, V1 and V2. Then we do our usual methods. We've got conservation of linear momentum. 7m plus 6m must equal mv1 plus 2mv2. Cancel the m's and we get 13 equals v1 plus 2v2. A nice connection between v1 and v2. Then we need to consider Newton's law of restitution. The speed of separation divided by the speed of approach is equal to the coefficient of restitution, which we're told is 0.5. So if I rearrange that quickly, we get v2 is equal to 2 plus v1. Then we can solve these simultaneously. So this becomes v1 plus 4 plus 2v1. 13 minus 4 is 9, is equal to 3v1. So v1 is equal to 3. Putting that back into here tells us v2 is now equal to 5. So after the first impact, particle A is now travelling with a speed 3 meters per second, particle B at a speed of 5 meters per second, particle B goes on to collide with particle C, And now I'm going to do that. So I'll put a little divide line down here. So we've got particle B at 2m, particle C with 3m mass. Particle B is now moving with 5 meters per second in this direction. Particle C is still moving with 1 meters per second. Then we've got after the collision. So we've got W1 and W2. General convention would say try to avoid using the things you've already used to mean something different, but I think in an exam you would probably get away with that so long as you were very clear about the division between the two parts of the question. So again, we've got conservation of linear momentum. This time we've got 10m plus 3m is equal to 2m w1 plus 3m w2. Cancelling the m's, we get 13 again is equal to 2w1 plus 3w2. Then on to Newton's law of restitution. Speed of separation, w2 minus w1 divided by the speed of approach, which is 4 again by coincidence, and that in this case has to equal 0.25, the coefficient of restitution between B and C. Multiplying by 4 gives us a 1, so we've got w2 is equal to 1 plus w1. Substituting that back into here, this becomes 2w1 plus 3w1. 13 minus 3 gives us 10 on the left is equal to 5w1, so w1 is equal to 2. Putting that back in here, w2 we can see must equal 3. So the final answer of the question, find the velocities of the three spheres after the second collision. After the second collision, A has velocity 3 meters per second. After the first collision, that did not change. A was not involved in the second collision. So that's still the velocity of A after the second collision. B was involved in the second collision, so although it was 5 for a moment, it is now 2. So B has velocity 2 meters per second after the second collision, and C has velocity 3 meters per second. So this is the answer to part A. Part B, I won't write this out, but I'll talk it through. Explain how you can predict that there will be a further collision between A and B. Very simply, they're all still moving in the same direction, and A has a greater speed than B. So eventually A will catch up to B, and they will collide again. So the two key elements of that explanation would be they're still traveling in the same direction, and A has a greater speed than B. Next example. A uniform smooth sphere P of mass 3m is moving in a straight line with speed u on a smooth horizontal table. Another uniform smooth sphere Q of mass m is moving with speed 2u in the same straight line as B, but in the opposite direction. So we've got P with 3m moving with speed u in this direction, Q of mass m with speed 2u moving in the opposite direction. The two spheres collide directly. The velocities of P and Q after the collision are v and w, respectively, measured in the direction of motion of P before the collision. So they're measured in this direction, and they are telling us the variables to use. So we've got v for P and w for Q. Now, although they're measured in this direction, that does not necessarily mean that the particles are traveling in this direction. We could still find that one or other of these has a negative value and therefore is traveling in the other direction. The coefficient of restitution between P and Q is E. Find expressions for V and W in terms of U and E. So we're going to go through the same process as usual. Conservation of linear momentum. To get one equation, we've got 3mu minus, because it's going the other direction, 2mu is equal to 3mv plus mw. The m's can cancel, and on the left we can simplify to u. Newton's law of restitution, speed of separation, w minus v divided by speed of approach, 3u, must equal the unknown value e, which gives us the equation w equals 3eu plus v. Now we can put these two together to get u is equal to 3v plus w, which we now know is 3eu plus v. U minus 3eu is equal to 4v. We could factorize out the u if we wanted, and then divide by the 4. To get an expression for v. Now we also know that w is equal to v plus 3eu. So if we just take this now and add 3eu onto it, and to combine this and keep the bracket, I'm going to factorize out u over 4, so the u goes here, and this becomes a 12e. 12e minus 3e is plus 9e. So a little bit of manipulation there just to keep the same format. Gives me 1 plus 9e with a u over 4 in front for w. So we've got two answers here for part A. Put those up on the top here in case we need them. On to part B. Show that if the direction of motion of P is changed by the collision, then E must be greater than 1/3. So if we go back for a second, the direction of motion of P is this. If it's changed, if it's going back this way, measured with this as positive, then V must be less than 0. That's our starting inequality. So this is telling us that V is less than 0. And we know V is the velocity of P, that's this one here. So this expression must be less than 0. We know u is a positive number, so we can divide by the u, multiply by the 4, and we still have 0 over here. Divide by 3, and we get 1/3. E must be greater than 1/3. Moving on to part C. More information here. Following a collision with P, the sphere Q then collides with and rebounds from a vertical wall, which is perpendicular to the direction of motion of Q. The coefficient of restitution between Q and the wall is E prime. Given that E is equal to 5/9, and that P and Q collide again in a subsequent motion, that means after Q has hit the wall, show that E prime must be greater than 1/9. Okay, let's dissect this just for a second. We're being told that E is now a fixed value 5/9. We weren't sure what that was before, now we are sure. That means I can put it into here and get, in terms of u, the velocities of P and Q after the first collision. So we know in terms of u, the velocity of Q after the first collision, that's the velocity it's going to have when it hits the wall. So before we do anything else, I'm going to work out the values in terms of u of these two. So the velocity of P, which we've been calling v in the work in part A, is u over 4 times 1 minus 3 times 5/9, so that's 5/3, which gives us minus u over 6. So the motion of P was reversed, it's moving away from Q and the wall. For W, which was the velocity of Q, if I put that in 5/9 for E, we get u over 4, 1 plus 5, so that's 3u over 2. So after the first collision, the direction of motion of P is reversed, it starts going back this way, and the direction of Q is reversed, so it's now going this way, and as it travels this way it hits a wall, bounces back off the wall, and comes back this way. That's what we're looking at now. So we've got Q, still with mass m, moving this way with speed 3u over 2, hitting a wall before the collision. After the collision, still mass m, it's now moving this way, and we need to multiply by the coefficient of restitution, E prime, to figure out this speed here. We don't know what that is yet, but it's 3e prime u over 2, whatever E prime is. Now to figure out that this is greater than 1/9, we need to use this information here. P and Q collide again. We know P is moving in this direction because of the negative here. We can see as well that Q is also moving in this direction, and I could put a little negative here as well if I wanted. The key point though is that Q catches up with P if they're going to collide again. So this value here, the speed, the magnitude of this, must be bigger than the magnitude of this. So all of that together tells me that 3e prime u over 2 must be greater than u over 6. If it wasn't, then q would never catch p and they would never collide again. U we know is a positive constant, so we can cancel that, get a 1. So e prime does indeed need to be bigger than 1 over 9, as they said in the question here. Next example. A tennis ball, which may be modelled as a particle, is dropped from rest at a height of 90 centimeters onto a smooth horizontal plane. The coefficient of restitution between the ball and the plane is 0.5. Assume that there is no resistance and that the ball falls under gravity and hits the plane at right angles. So we've got a plane here, the ball starting at rest, falls 90 centimeters. Immediately I'll change that into meters. Coefficient of restitution 0.5, and that will stay the same throughout the question because we're going to be using the same ball and the same plane for each part of the question. Find the height to which the ball rebounds after the first bounce. So it's going to come down, it's going to hit the ground, rebound, and then of course it will be going up again to a certain height, let's say here. The two separate bits here are using constant acceleration, and the coefficient of restitution is important between them because as we get this final speed here just before it hits, we need to apply the coefficient of restitution to find out what the rebound speed is here immediately after the collision to find how far up it goes. So in red we've got u is equal to 0. If I take downwards to be positive, then I'll say a is equal to g, and I'll use g instead of 9.8 because we're going to be doing a few different things here. I can put 9.8 in whenever I need a final numerical value. S is equal to 0.9, and what we need to find is v, the speed just before it hits. To do that, we're going to use v squared is equal to u squared plus 2as. U squared is 0, 2 times g times 0.9, so v squared is equal to 1.8g. V is the square root of that. Now the important thing to remember is to apply the coefficient of restitution to find the rebound speed immediately after the collision. So here we've got a root of 1.8g, and we need to multiply that by e, which is a half. So in yellow, in this situation here, our starting speed, I'll take upwards to be positive here, is a half square root 1.8g. A is still going to be g, but negative g now because I've changed which direction I'm using as positive. V, when it comes to the top, will be instantaneous rest, and the question here is what is s? How far up? So we're going to use the same formula. V squared equals u squared plus 2as. Here v squared is 0, u squared is 1 over 4 times 1.8g plus 2 times minus g. So let me change that to a minus 2gs. I can divide everything through by g to cancel those, bring the 2s on the other side, divide by 2, and that gives me 1.8 over 8, which is 9 over 40 meters. So that's the height it comes back up to after the first bounce. Part B, find the height to which the ball rebounds after the second bounce. Now this is exactly the same sort of question, except instead of starting at 0.9, it's now going to have to start at 9 over 40. At least we already know the speed, because if there is no resistance, the speed it goes up initially here is the same speed it will hit the ground again as it comes back down, 1/2 square root 1.8g. So as we go to the second bounce, we need to know how fast is this coming up, how high does it come on this bounce. Again, I'll take upwards as positive here, and I need u by applying the coefficient of restitution, which is going to be 1/2 of this value. So it's 1/2 root 1.8g times another 1/2. So the speed here initially is 1/4 of the square root of 1.8g. A is still going to be minus g, v is still going to be 0 at the top of this bounce, instantaneous rest. And the question is, what is the height? Same formula, v squared equals u squared plus 2as. 0 equals now 1 over 16 times 1.8g minus 2gs. Again, the g's cancel. Take the minus 2s on the other side, divide by 2, we get s is equal to 1 over 32 times 1.8, which is 9 over 160 meters, which is just a little bit more than 5 centimeters. Part C. Find the total distance travelled by the ball before it comes to rest according to this model. So we've got the height here, 0.9, and then this height, 9 over 40, and then this height again as it comes back down, 9 over 40, plus this height, 9 over 160, plus this height again, 9 over 160, and then the next one, and the next one, and the next one. And of course we're not expected to calculate all of those. We're expected at this point to find a pattern and use a series calculation. So I'll take the key numbers onto the next screen. We've got 0.9, 9 over 40, 9 over 160. So we're adding these together. 0.9 plus 9 over 40 as it comes up, plus 9 over 40 again as it comes back down, and then 9 over 160 as it goes up, plus 9 over 160 as it comes back down, and so on. This is the information we've got, and we need to find the pattern of the series in order to find the sum. Going back here for a second, the pattern is the fact that we're multiplying by a half on this each time. That then in the formula is being squared each time. So from here to here we have a quarter multiplier. So you can see 9 over 40 times 1/4 is this, and if you change this 9 over 10 times by a quarter, you get 9 over 40. So each of these is being multiplied by a quarter. So in terms of a geometric series, this gives us r is equal to 1 over 4. I'm going to manipulate this a little bit though, and not choose this as my starting number, because this is the only one that is not doubled up. So I'm going to put this as 0.9 plus 2 lots of the series 9 over 40 plus 9 over 160 plus ... Then for the geometric series, I can make a is equal to 9 over 40. Find the sum of this, multiply it by 2, and add the 0.9. If you remember, the sum of a geometric series to infinity is equal to a over 1 minus r. So we've got 9 over 40 divided by 1 minus a quarter, which gives us 3/10. So the part in brackets here is equal to 3/10. So that gives me 0.9 plus 2 times 3 over 10, which is 6 over 10 or 0.6. 0.9 plus 0.6 is 1.5 meters in total. So although the maths involved in this question isn't that difficult, it's quite a difficult question because right in the middle of impulses and collisions you're being expected to recognize a geometric series. The final part of the question then, criticize this model with respect to the motion of the ball as it continues to bounce. A question like this is asking you to find something that's not very realistic about the model. In this case, an infinite geometric series suggests that there are an infinite number of bounces, because as we continue this pattern, we'll never actually get to 0 height. It will never really come to rest, which is why we had to take it to infinity. As with many of the written answers, I won't write this out, but your answer would be something like, the model assumes an infinite number of bounces, which is not realistic. And that brings us to the end of the examples in the textbook. What I've got now are just 2 final exam questions. First one you will probably recognize from a previous video. We've already done A and B, so I won't do those. But I wanted to show that this exam question as a whole was based on successive impacts. There was a second collision here. So we'll do this, and then we'll finish with a full exam question on the next screen. So we had 3 particles, they had the masses here, there was a collision between the first 2, and we had to show that the speed of q, the middle one, after the collision was this. Then we had to find the range of values for p for which the direction of motion is reversed, and we found that for that to happen, k had to be bigger than 27. Now we're told, following the collision between P and Q, there is a collision between Q and R, so we're using the speed of Q after the first collision. The speed of R initially is at rest, and we're given that K is equal to 7. Don't worry that that's not bigger than 27. Remember, this was specifically talking about if the direction of P was reversed. So here now we're told K is 7, that means that the direction of P was not reversed. But that won't have any effect on our question here. We're just going to look at Q and R. So the key point here is that Q is going at speed this, where we now know K is 7. So if K is 7, then this becomes U over 3. So Q is moving with U over 3 speed, and the mass of Q was Km. We now know that that is 7m. R, as we were told at the very beginning of the question, is at rest and has mass 7.5 m. The question we're answering, find the total kinetic energy lost in the collision between Q and R. So we need to know the kinetic energy before the collision. We can do that fairly easily here. We also need to know the kinetic energy after the collision, so we need to know the speed of the two particles after the collision, which means we go through our usual process. Q and R after the collision. We're also told that Q is brought to rest by the collision with R. So Q at the end of this has 0 meters per second for its speed, and R has the unknown V. So we don't need to worry that we don't know the coefficient of restitution between Q and R. We won't need it. We only have one thing we don't know, so the conservation of linear momentum will be enough. If I squeeze that in the bottom here, we've got 7mu over 3 for particle Q, plus 0 for particle R, has to equal 0 for particle Q, plus 7.5 mv for particle R. The constant n cancels out. That gives us V is equal to 14u over 45. And that's enough information to find the kinetic energy. So the kinetic energy before the collision between Q and R is a half times the mass of Q times the speed of Q squared, plus 0 for R because it's got 0 speed, gives 7mu squared over 18. The kinetic energy after the collision is 0 for Q because it's got 0 speed, plus a half times mass times speed squared for R, which is 49mu squared over 135. To find the energy lost, then we need to do 7mu squared over 18 minus 49mu squared over 135, and that gives us a final answer of 7mu squared over 270 joules of energy lost in the collision. That finishes off that exam question from the previous video. Now a full exam question to finish off this chapter. Two particles A and B move on a smooth horizontal table. The mass of A is m, the mass of B is 4m. Initially A is moving with speed u when it collides directly with B, which is at rest on the table. As a result of the collision, the direction of A is reversed. Coefficient of restitution is E. Find expressions for the speed of A and the speed of B immediately after the collision. Okay, before we do anything else, let me quickly underline we want expressions for the speed, not the velocity. So, although the velocity is what I'm going to find, at the very end of this first part, I need to make sure I've got speed as my final answer. Let's set up the problem. We've got A mass m, B mass 4m, initially B is at rest, and A is moving towards B with speed u. After the collision, the direction of motion of A is reversed, but I'll call it V for now in this direction, and B obviously moves off in the positive direction, call that V2. So we do all our usual things. Conservation of linear momentum, mu plus 0 equals mv1 plus 4mv2. The m's cancel, and we get a nice relationship between these two. Newton's law of restitution, speed of separation, v2 minus v1 over speed of approach, u must equal e. Rearrange that, and we get v2 is equal to eu plus v1. Putting those two together, we get u is equal to v1 plus 4 lots of v2, so that's 4eu plus 4v1. U minus 4eu is equal to 5v1. If I factorize out the u, 1 minus 4e, divide by that 5, we get an expression for the velocity of A. The velocity of B is v2. v2 is equal to this v1 plus eu. So as I've done before, I'll factorize out the u again, and I'll force out a 1 over 5 that isn't here to make this a 5e inside the bracket. Minus 4e plus 5e is plus e. So we get u over 5, 1 plus e as an expression for the velocity of v2. So these two are velocities still, and we need speed. Now the easy way I could do that is just to put a modular sign around it like this, and around this one like this. And now I've got speed for both. But if we look at it just a little bit more closely, we can see that it's not really necessary for v2, because we know v2 is going to have to move this direction if it started at rest, and I've called that direction positive. So this will be a positive value. We also know for sure that the direction of motion of A is reversed. So that tells us that the value for v1 will be negative. And that's a problem for speed. We do need the magnitude symbol here. But because we know this will be negative, and that must be coming from this bracket, what we can consider the modular sign to do is to switch this around and make it 4e minus 1. So if you didn't want the modular symbol there, you could then write that as u over 5, 4e minus 1. And down here, as I said, the modular symbol isn't really necessary. That will equal the same thing. So this is the velocity, and this is the speed, because this is definitely going to be a positive value, because this is definitely going to be a negative value, which we know from the question. So the final answer to part A is this expression and this expression. In subsequent motion, that means after everything that's happened so far, B strikes a smooth vertical wall and rebounds. So there's a wall over here somewhere, B is coming this way, hits the wall and bounces back. The wall is perpendicular to the direction of motion of B. The coefficient of restitution between B and the wall is 4 over 5. Given that there is a second collision between A and B, show that this is true. So this is quite similar to one of the examples we did from the textbook. We're looking at a completely different impact here, so I'll redraw it up here. We've got B, 4m, coming this way with speed u over 5, 1 plus e. It's going to hit a wall. After the impact, it's going to rebound from the wall, and it's going to go this way with this speed multiplied by the coefficient of restitution between B and the wall. So the speed coming this way is going to be 4u over 25, 1 plus e, because I've just taken this and multiplied it by 4 over 5. I've put the arrow on, but I will also just put a little negative because I'm still taking this way to be positive. That now is the velocity, not the speed. Given that there is a second collision between A and B, as before, what this means is if they're both going this way, which they are, this speed must be greater than this speed here. So to make this a speed, I'll just take that negative off again, and I've already made this a speed rather than a velocity. So the speed 4u over 25, 1 plus e, must be greater than u over 5, 4e minus 1. Otherwise, B would not catch up with A, and it would not be able to collide a second time. So I can cancel the u's. If I open the bracket on the left here with the 4, we get 4 plus 4e. Take the 25 on the other side, cancel it with the 5, that gives us a 5 to open this bracket, giving us 20e minus 5. Bring that over here brings us a 9 and 16e. So e must be less than 9/16, which is the right-hand side of the inequality here. But we still have this left-hand side here. How do we know that e must be greater than 1/4? That goes back to the first part we were told about a. The direction of motion of a is reversed. We know it must be reversed, so v1 must be negative, and we talked about that because we changed this into this. We know that 1 minus 4e must be a negative value, otherwise this velocity in here would not be negative and it wouldn't be reversed. But we know it is, so we also know from here and here that 1 minus 4e must be a negative value. So 1 must be less than 4e, and e must be greater than 1/4. Putting these two together gives us our final answer as given in the question of this. Part C. Find the total kinetic energy lost in the first collision between A and B. So we don't need to worry about any of this. We're just going back to the first collision, kinetic energy here, and the kinetic energy here, find the loss. Given that E is 1/2, we can put that in here and here to find the speeds in terms of u. 4 times 1/2 is 2, minus 1 is 1, so that's just 1 times this. So this becomes u/5. And down here, 1 plus 1/2, 3/2, times u/5 is 3u/10. So now we do our usual kinetic energy process. Kinetic energy before the collision is 1/2 times the mass of A times the speed squared of A plus 0 for particle B because it's not moving is 1/2 mu squared. Kinetic energy after is 1/2 times m times u/5 squared plus 1/2 times 4m times 3u/10 squared. And that equals 1/5 mu squared if you do all of that. So the kinetic energy lost is equal to 1/2 mu squared minus 1/5 mu squared, and just squeeze it in here, is 3 mu squared over 10 joules of energy lost in the collision. So we've got part A over here, part B up here, and part C in here. Quite a lot of examples there. I hope that has been enough for you now to have a go at the questions in exercise 5e and the chapter 5 review exercise, and maybe I'll see you for the final chapter in this module, chapter 6, in the next video.